Hello everyone. In this class, I am going to discuss the basics of multivibrators, and this topic is in the subject integrated circuits. Fine. So in this particular class, I will discuss about the different types of multivibrators, and also will discuss about the triangular wave generator. So contents are basics of multivibrators, astable multivibrator, monostable multivibrator, and triangular wave generator. Now starting with the multivibrator. So firstly we need to understand that what is multivibrator. As the name suggests, multivibrator. Multi means more than one. Vibrator means the output state vibrates between different states. It means that a circuit which vibrates, which changes its state, that is called multivibrator. Multivibrators are of three types. The first one is astable multivibrator. The second one is monostable multivibrator. And the third one is bistable multivibrator. So, astable multivibrator. Starting with the astable multivibrator. Astable multivibrator is the multivibrator which is having no stable states. Which is having no stable state. It means that the output of the astable multivibrator, it continuously changes its state from low to high, high to low, low to high, high to low. So, at the output of the astable multivibrator, what we get? We get a pulse waveform, square waveform. In the pulse waveform, you can see that there are only two values, high and low, high and low. So, continuously the output is changing. So, it is producing the pulse waveform. So, the output of the astable multivibrator is pulse waveform, square waveform. That's why astable multivibrator, it is also called square wave generator. Square wave generator. And it's an oscillator which is used to generate a square wave of a particular frequency. So it means that this astable multivibrator or square wave generator, it does not require any input. So the second important point about the astable multivibrator is no input is required. We don't apply any input to the astable multivibrator. And without input, it produces the output because of the noise present in the circuit that you had studied in analog circuits, in oscillators, right? In oscillators, we don't apply any input, and without applying input, we get the output because of that noise. As far as monostable multivibrator is concerned, monostable multivibrator, as the name suggests, mono means one. So monostable multivibrator is the multivibrator which is having one stable state, and the other state is quasi-stable, kind of unstable. Other state is quasi-stable. But in monostable, only one state is stable. So, what is the function of monostable multivibrator? The function of the monostable multivibrator is, it is used to generate a pulse of a particular duration. For example, since in monostable, there is only one stable state. Let's say if logic 0 state is the stable state, then when we apply the trigger input to the monostable multivibrator, then the output of the monostable multivibrator, it changes from logic 0 to logic 1, and it remains in logic 1 for a particular time duration, and after that automatically it comes from high to low, and this duration is t. So from here you can see that this logic 0 state is the stable state. Why it is stable state? Because when the circuit is in logic 0 state, it does not come from logic 0 to logic 1 automatically. It comes from 0 to 1 only when trigger input is applied. If the trigger input is not applied, then it will remain in its stable state, that is logic 0. Similarly, logic 1 can also be the stable state, fine. But only one state will be stable at a time. So in this case, I have assumed that logic 0 state is the stable state. And when the trigger input is applied, then the output comes from logic 0 to logic 1 state. And it remains in logic 1 state for the time duration t. And after completing that time duration t, it automatically comes from high to low. It means that it automatically comes to its stable state. So here in this case, logic 0 is the stable state, but logic 1 is not stable, because the output of the multivibrator, it remains in logic 1 state only for a particular time, and after completing that time, it comes to its stable state. In this case, we have taken that stable state is logic 0. So the function of monostable multivibrator is used to generate a pulse of a particular duration. It means that we can turn on or turn off any device for a particular time with the help of monostable multivibrator. For example, if we want to turn on the motor, if we want to glow the LED for a particular time, then we can use monostable multivibrator. And this time t is decided by the passive elements, which depend upon the external components connected. That external component connected is resistor and capacitor. By changing the value of resistor and capacitor, we can change the time duration of the pulse. Fine. And another important point about monostable multivibrator that I have already mentioned, that is trigger input is required. Trigger input is required. So you can see the difference between stable and monostable multivibrator. In stable multivibrator, there is no stable state. In monostable multivibrator, there is one stable state. In stable multivibrator, no input is required. But in monostable multivibrator, input is required. That input is the trigger pulse, trigger input. Fine. Now coming to the next multivibrator, that is bistable multivibrator. As the name suggests, bi means two. So bistable multivibrator is the multivibrator which is having two stable states. Two stable states. And the example of bistable multivibrator is flip-flop. Flip-flop, which you have studied in digital design. Flip-flop is a bistable multivibrator. Why? Because flip-flop is having two stable states, that is logic 0 and logic 1, and the output of the flip-flop, it changes only when there is a clock pulse, when there is a trigger pulse. And in flip-flop we use edge triggering, right? So you remember, in flip-flops clock is required, and that clock should be edge triggered. So the example of bistable is flip-flop that you have studied in digital design. So these are the types of multivibrators. Now starting with the astable multivibrator. See, we can design a stable multivibrator using 741 op-amp IC, as well as we can design this astable multivibrator using 555 timer IC also. Similarly, monostable multivibrator can be designed with the help of 741 op-amp IC as well as with the help of 555 timer IC. In this class, I am going to design this astable multivibrator using 741 op-amp IC. Fine. So let me draw the circuit. Firstly, we have taken this operational amplifier op-amp, and in oscillator positive feedback is required, right? And it is an oscillator, basically a stable multivibrator. It is also called a square wave generator, and that positive feedback is given to this op-amp with the help of a voltage divider circuit that is formed with the help of two resistors. Let's say these resistors are R1 and R2, and the junction point of R1 and R2 is connected to the non-inverting terminal of the operational amplifier. So this R1, R2, it provides a positive feedback. And one capacitor is connected to the inverting terminal of op-amp C. that will continuously charge and discharge, but capacitor will discharge only when it will get the discharging path. Now the issue is that you can see that the discharging for the discharging path for the capacitor is only this inverting input terminal, but we know that the input impedance of op-amp is very high. So to provide the discharging path, what we do, we connect a resistor in the feedback, the resistor R. So this is a circuit of stable multivibrator using 741 op-amp IC, and if it is 741 IC, then it means that it requires two power supplies. The first one is plus VCC and minus VCC. Now you can see that we have not applied any input. We have not applied input. Power supply is not the input. It's just to bias the op-amp, right? We have not applied any input, but it generates output. And since positive feedback is used, so the output of the op-amp will get saturated. Output of the op-amp will get saturated also in the open loop configuration of op-amp. So you people had studied that circuit, that application. That application is voltage comparator. In open loop configuration, op-amp has very limited applications. The reason is in the open loop configuration of op-amp, the output gets saturated. Means at the output, there will be only two values, plus Vset or minus Vset. So there are very limited applications in open loop configuration, and one of them is voltage comparator circuit. But op-amp will get saturated also in case of positive feedback. Fine. So let's say if the op-amp output is at plus Vset, it is at plus Vset. The op-amp output, it can be either at plus Vset or minus Vset. Let's take if the op-amp output is at plus Vset. And one more thing, output will be at plus Vset when the voltage at the non-inverting terminal, that is the positive input terminal, it is higher. If it is higher than negative input terminal, then output will be at plus Vset. Otherwise, if the inverting input terminal voltage is greater than non-inverting, then the output will be at minus Vset, right? So to understand the working, we have taken output is at plus Vset. When the output is at plus Vset, then you can see that what will be the voltage at the non-inverting terminal? What will be the voltage at the non-inverting terminal? The voltage at the non-inverting terminal, you can see it's a voltage divider circuit. It will be R2 upon R1 plus R2 into plus Vset. Let's say we take, if we take R2 upon R1 plus R2 with beta, if we replace R2 upon R1 plus R2 with beta, then the voltage will be plus beta Vset, right? Plus beta Vset, where beta is R2 upon R1 plus R2. So we don't want to write again and again R2 upon R1 plus R2. That's why we have taken it. We have replaced R2 upon R1 plus R2 with beta. See, when the output is at plus Vset, then the voltage at the non-inverting terminal is plus beta Vset. And this capacitor C will start charging. Capacitor will start charging. Let's say the capacitor voltage is Vc and this Vc is at the inverting terminal. If it starts charging, it means that Vc will start increasing. Vc will start increasing, and when Vc, capacitor voltage, crosses plus beta Vset, then the output of the op-amp will come from plus Vset to minus Vset, right? So I repeat, when Vc, capacitor voltage, it exceeds plus beta Vset, then the output of the op-amp will switches from plus Vset to minus Vset. Reason? Because when Vc exceeds plus beta Vset, then at that moment, the voltage at the inverting terminal will be higher. And when the voltage at the inverting terminal will be higher, then the output will be at minus Vset. When the output is at minus Vset, now this capacitor C will start decreasing. It starts decreasing. Decreasing means Vc will decrease. It will discharge, in fact. Capacitor will get discharged. And with the help of resistor R. So Vc will decrease. Vc will decrease and decrease. And when Vc becomes lower than minus beta V set, because when the op-amp output is at minus V set, then the non-inverting terminal voltage, it will be at minus beta V set. Now when Vc becomes lesser than minus beta V set, it means that at that moment the voltage at the non-inverting terminal will be higher. Then again the output of the op-amp will come from minus V set to plus V set, and this process will repeat. When the output will be at plus V set, then again the capacitor will start charging, and when the output of the op-amp is at plus V set, then the voltage at the non-inverting terminal will be at plus beta V set. And when it is plus beta V set and the Vc is increasing, and when Vc exceeds plus beta V set, then output will come to minus V set. And when the output will come to minus V set, in that case, capacitor C will start discharging. It means that Vc will decrease. And when the output is at minus V set, then the non-inverting terminal voltage is minus beta V set. And Vc is decreasing. When Vc is decreasing and Vc becomes less than minus beta V set, then again the output will come to the plus V set. So this process will be repeating. Fine. It means that capacitor will be charging and discharging, charging and discharging. Output will get switched from plus V set to minus V set, minus V set to plus V set. And when we draw the waveform of this stable multivibrator, that is the output voltage. Let's say this is V0 versus T. Then V0 is simply a pulse waveform, a square waveform. Okay. So the peak voltage is plus V set and the negative peak is minus V set. So this is the output waveform. And if we draw the capacitor voltage waveform, then you can see that when the output is at plus V set, then capacitor is charging, and when the output is at minus V set, then capacitor is discharging. When the output is at plus V set, again the capacitor is charging. When the output is at minus V set, again capacitor is discharging. And the capacitor charges and discharges between the voltage level, that is, it is minus beta V set, and this one is plus beta V set. Why plus beta V set and minus beta V set? Because the non-inverting terminal is fixed at plus beta V set or at minus beta V set, depending upon the output voltage. If the output is at plus V set, then the non-inverting terminal voltage is plus beta V set. If the output is at minus V set, then the non-inverting terminal voltage is minus beta V set, where beta is R2 upon R1 plus R2. So this is the capacitor voltage waveform Vc. Now we can derive the frequency of this square wave pulse waveform, because in oscillator, in multivibrators or stable multivibrator, we are interested in the frequency of the output signal F0. So here what concept we use to derive the frequency of the square wave? See, this is one cycle. Let's say time period is T, and this is the half cycle. Let's say this is time T1. If we anyhow calculate the value of T1, if we get the T1, then what will be T? T will be equal to 2 into T1. If we get T, then what will be the frequency of the square wave pulse waveform? That is 1 by T. So we can get the frequency of the square wave. That's why it is called a square wave generator. So ultimately we need to calculate the value of T1. Once we get T1, we can simply calculate T, that is 2 into T1. Once we get T is the time period of one cycle, then what will be the frequency? 1 by T. Fine. So to calculate T1, we need to use capacitor voltage equation that you people had derived in network analysis, that is Vc is equal to Vf plus Vi minus Vf into e to the power minus T by Rc. Now see, this Vc is the capacitor voltage, Vf is the final value, that is T equal to at T equal to infinite, Vi is the initial value. Now see, Vc is equal to final value at the capacitor, it is V set, initial value of the capacitor voltage that you can see here from the waveform, the initial value Vi is minus beta V set. So Vi is minus beta V set, Vf is V set, e to the power minus T by Rc. Fine. From here, what will be Vc? Vc will be, from here we can Vi, this Vi is actually minus beta V set, right? So just take common Vset. So minus Vset is equal to beta plus 1 into e to the power minus t by RC. Fine. Now see, at time t is equal to t1, what is the value of Vc? Just see the waveform. At time t equal to t1, see it. At time t equal to t1, the capacitor voltage is plus beta Vset. So at t equal to t1, Vc is equal to plus beta Vset. Now we can put Vc is equal to plus beta Vset is equal to Vset minus Vset beta plus 1 e to the power. Small t will be replaced with t1. Now from this equation we can calculate t1. You can get t1 after rearranging the terms. T1 will be RC ln 1 plus beta upon 1 minus beta. You can just rearrange the terms, you will get the value of t1. So from here what will be t? T will be equal to 2 into t1, and this t will be equal to 2 RC ln 1 plus beta upon 1 minus beta. So from here we can calculate the value of f0. F0 will be equal to 1 by t. Now to make this equation simpler, what we can do, just take R1 is equal to 1.16 R2. This we are doing for mathematical simplification, and if we are taking R1 equal to 1 plus 1.16 R2, then the frequency F0 will be equal to 1 upon 2 RC. That you can do it yourself. Fine. Why we are doing it? We are doing it just to simplify the frequency equation. Right? Now after doing this, you can see that there is no ln term in the output frequency, but remember that we are getting 1 by 2 RC when you are taking R1 equal to 1.16 R2. So coming to the circuit, what we are doing? We are doing R1 is equal to 1.16 R2. So practically when you do this circuit, when you implement this circuit, then you need potentiometer for that. Fine. So the final equation, we have calculated the frequency of the square wave. Now coming to the monostable multivibrator. Monostable multivibrator. In monostable multivibrator, let me draw the stable multivibrator circuit again. From there, we will see that how to make the monostable multivibrator circuit. See again, we are providing the positive feedback with the help of potential divider R1 and R2. Junction point of R1 and R2 is connected to the non-inverting terminal, and at the inverting terminal there is a capacitor C connected, and to provide the discharging power we have connected this resistor R. Fine. So this circuit is a stable multivibrator. Now we need to design monostable multivibrator. And one difference between astable and monostable is that in monostable we require input. That input is the trigger input. Fine. So what we do, we apply that trigger input at the non-inverting terminal. We apply the trigger input at the non-inverting terminal, and in parallel with the capacitor C, we connect a diode D. We connect a diode D. So diode D is connected in parallel with capacitor C. So what is the function of diode D? Assuming this is a silicon diode. Due to this diode D, the capacitor voltage Vc will clamp to 0.7 volt. Fine. We are connecting a diode in parallel with capacitor. Then since the capacitor is in parallel with diode, then the capacitor voltage Vc, it will be clamped to 0.7 volt for silicon diode. Fine. Now, see how this circuit works. In monostable multivibrator, one state is stable. It may be logic 0, it may be logic 1. For example, let's say logic 1 state is stable. That means logic 1 state means plus Vsat state is stable. So the output of the monostable multivibrator will remain at logic 1, that is plus Vsat. And when we apply a trigger input, now when we apply the trigger input, we need to take care of few things. Fine. Since the stable state is plus Vset, and we need to apply the trigger pulse such that the output should come from plus Vset to minus Vset. And from this circuit, you can see that the voltage at the inverting terminal is 0.7 volt because Vc is 0.7 volt. Now, and further, output is at plus Vset in the stable state. So, what will be the voltage at the non-inverting terminal? It will be plus beta Vset. What is beta? Beta is R2 upon R1 plus R2 that I have already mentioned. Now, if we want that the output of the circuit should switch from plus Vset to minus Vset, for that, the inverting terminal voltage should be higher. It means that inverting terminal voltage is 0.7 volt and the non-inverting terminal voltage is plus beta Vset, and we need to apply the trigger pulse. Let's say the magnitude of the trigger pulse is V1. So in this case, we can see that we need to apply the negative trigger pulse, and let's say that magnitude is minus V1. So this voltage plus beta Vset minus V1, it is the voltage at the non-inverting terminal, where V1 is the magnitude of the trigger pulse, and we are applying the negative trigger. Why? Reason is we need to make sure that 0.7 volt should be greater than this quantity, because when it happens, then voltage at the inverting terminal will be higher, and if the voltage at the inverting terminal will be higher, then the output will switch from plus Vset to minus Vset. And when the output is at minus Vset, then this diode D will be off. You can see that diode D will be off. It will be reverse biased. It will be in reverse biased. So it means that D is off. D is open switch. Now capacitor C will start discharging. If it starts discharging, and as the voltage at the inverting terminal becomes less than non-inverting terminal, then automatically the output of the circuit will come again to the plus Vset state, that is the stable state. Now see, in this case, logic 1 state is the stable state, and the circuit, the output of the monostable multivibrator is at plus Vset. It goes from plus Vset to minus Vset only when we are applying the trigger input at the non-inverting terminal. And the magnitude of the trigger input, it should be such that the right hand side, that is 0.7 volts, should be greater than left hand side. Only then the voltage at the inverting terminal will be greater, and when it will be greater, then output will come to the minus Vset. And once the output comes to minus Vset, it means that diode D will be reverse biased. It will be off. Means capacitor C will start discharging. Means Vc will be decreasing. If Vc is decreasing, and when Vc becomes less than non-inverting terminal voltage, then again the output will come to plus Vset. And when the output will come to plus Vset again, then again this diode D will be forward bias. Once diode D is forward bias, then again the capacitor voltage Vc will be clamped to 0.7 volt for silicon diode. Fine. So in this case, we can see that one state is stable. So when we do the derivation part and when we calculate the time duration T, then this T comes to 0.69 RC. R and C are connected in the circuit, and we get this equation when we assume that Vsat is very greater than Vd, where Vd is the voltage drop across the diode, and Vsat is the saturated voltage, that is approximately equal to supply voltage, but obviously it is less than supply voltage, but it is higher. Fine. So when we consider Vsat is very greater than Vd, Vd is the voltage drop across the diode, then we get the time duration of the pulse, that is equal to 0.69 RC. So this is about the monostable multivibrator. Now triangular wave generator. So we can easily generate the triangular wave if we get the square wave. We are getting the square wave with the help of a stable multivibrator. Now again draw the circuit of a stable multivibrator. In a stable multivibrator, there is a voltage divider circuit that is formed with the help of R1 and R2, and the junction point of R1 and R2 is connected to the non-inverting terminal. At the inverting terminal, there is a capacitor C connected, In the feedback path, there is a resistor R. So the output of this circuit is basically a square wave. Fine. And this is a stable multivibrator. A stable multivibrator. Fine. So with the help of a stable multivibrator, we are getting the square wave. So to get the triangular wave, simply integrate this square wave. So we need another op-amp, and let's say this op-amp is A1, this one is A2, and A2 should be integrated. So we are considering inverting integrator, means non-inverting terminal will be ground. At the inverting terminal, we are connecting a resistor. Let's say this resistor is R3 because we have already used R, R1, R2. And in the feedback of integrator, there is a capacitor. Let's say this capacitor is C1. So the output of a stable multivibrator is connected to the input of the integrator. This one is integrator. So when we integrate a square wave, we get triangular wave. So we can simply generate triangular wave. Just design a stable multivibrator and just integrate that square wave. You will get triangular wave. So this is all about this class. In this class, I have simply discussed the basics of a stable multivibrator, monostable multivibrator, and triangular wave generator. So there are various applications of a stable and monostable multivibrator, like a stable multivibrator that is used to generate a square wave, right? FSK generators, we can use we can use that a stable multivibrator. Monostable multivibrators, it can be used in missing pulse detector and pulse width modulation. Also, we use monostable multivibrator. Fine. So all these circuits which I have discussed today in this class, these circuits can be designed with the help of 555 timer IC also, that you will study in the last unit of integrated circuits. Thank you.